So the recording is starting. I'll just wait for the recording to start. All right, folks, welcome back to our introduction to AI, this course on neural networks, large language models, and generative AI. It's a pretty packed course in terms of content. We are going to teach you, as you must have figured out, rather weighty matters, and quite weighty, as you can see from the stack. Right? The subject is often called deep learning, and it's a deep stack of books. I'm kidding. So a bad pun, right? I'm told that there are jokes, and then there are bad jokes, and then there are dad jokes. So I fall into the dad jokes category. So because so many of you are new, I'll tell you a little bit about this course. Today, artificial intelligence, or introduction, we use the word artificial intelligence, whose heart is machine learning. So we learn machine learning. In particular, in this course, we focus on a class of algorithms that have become quite dominant because we have to pick and choose. Machine learning is a vast field where the algorithms have been growing for decades. In particular, this subject, as we talked about in the very first session, has its roots going back to the 1770s, 1780s, to Gauss formulating the first loss function, and so on and so forth. So it's a field that has deep roots. It is also a field that is vast, and many classes of algorithms and subfields exist in machine learning. We can't do all of it in the space of 3 months. So we are going to focus on a dominant algorithm these days, which is neural networks. And everything that we learn will be within the scope of that. Now, neural networks itself has become a vast field. It has grown. There are different so-called neural architectures. There are feed-forward networks, right, or dense networks, people call it, etc. Then there are, excuse me, convolutional networks. There are recurrent networks, right, recurrent neural networks, in which class you get all the LSTMs and GRUs, etc. And then you have autoencoders, you have generative adversarial networks, you're going to encounter UNets, you're going to encounter lots of things along the way. And then you have attention, you have transformers. Transformers themselves have encoders, decoders, aspects to them. It's a vast field. And then diffusion models, energy models, normalized flow models. So it's a vast field in itself, which means that in this workshop, we have a task. We have to lay good foundations, strong foundations. In the beginning, move slow so that we can move fast later. First, build the foundations, be sure of the foundations, and then rapidly get through all of these neural architectures with practical examples. That is how this course is designed. It's a 12-week course, though I may take the liberty to extend this course by an extra 2 weeks if we are not able to cover all the material. Right? Just a basic thing, we meet every Tuesday, 7 p.m. Pacific time, and unfortunately, midnight, 10 p.m. East Coast time. It is a time also friendly to people in India and to people in Malaysia. I know we have people from Malaysia, from India attending it. There are people from Eastern Europe attending. For them, it's a bit brutal. So I suppose we live in global times, and it's interesting to have participation coming from all over. Now, since we have a lot of new enrollment coming in late, I'll just quickly go over it. See, in this book field, there are many good books. As an educationalist, I also know that there are different learning styles. Some people learn from theory. They need very concrete math first before they get to anything, any examples. Some learn from code, samples of code, and by tinkering with it and seeing how it works. Right? There are people who learn sequentially. There are people who learn sort of like a puzzle. They want each topic to be self-contained. Right? These are, of course, the work done more than 4 decades ago by educational psychologists, Piaget, and so forth. There's theories about education. They still hold. So what I've done is for your I've not assigned one single textbook, which I think is a folly. There are 4 textbooks that cover essentially the same material, but with different perspectives or different emphasis. One of them is Deep Learning, a Visual Approach. Right? This book is quite visual, as in lots of examples and diagrams. If you look at any page, a very good book. Then the second book is very code-centric. It takes PyTorch, something that we will base on, PyTorch for all its code. And the title of the book is Math, Algorithms, and Models. Unlike books that are like the Mannings and the O'Reilly books, which I consider to be actually pretty bad books on deep learning, this book is a Manning book, and the best. It's really very good because unlike typical programming books, it not only gives you code, precise code, but it actually explains the math, the model, the algorithms in a uniquely insightful way. In fact, I've not found such explanations in any other textbook. Very accessible way. If you are a programmer, you would just delight. You will find it very comfortable to walk through the code. And then when it comes to the math, seamlessly it goes to the math. It explains it so intuitively, you'll hardly feel it. Okay? So that's the virtue of this book, Inside Deep Learning. And then there is the next book, Christopher Bishop's great classic, Deep Learning. Well, he wrote the book Machine Learning. Before he wrote that book, he wrote another book, Neural Networks, which is from the 80s or 90s, right? Which by now is somewhat dated, quite dated, but it's still worth a read. Then he wrote Machine Learning, which became a classic, pattern recognition and machine learning. And then and by this time, his son too has become a researcher. So both of them together have written this deep learning book that just came out. The virtue of this book is as contemporary, and the virtue of anything that Bishop writes is the utter clarity of explanation of the concepts, extremely well explained. For those of you who want to know who in the world is this Bishop, he used to lead machine learning at Microsoft for many years. Now he still leads one of their big divisions. He also happens to be a direct PhD student of an PhD under Peter Higgs. Does anybody know what Higgs is? Of the Higgs boson fame, right? So why do some things in the universe have mass? Like, for example, electrons, protons, neutrons, while photons don't have, light particles don't have. Well, you can blame it on Higgs, right? The Higgs field or the Higgs boson. So he literally is a direct student, and you can see that interpretation that comes from geometry and math, very, very clear. The theoretical physicist thinking, very clear in the way he writes the book. Now, some of you have pointed out that the way I explain things is also like this, but I tend to simplify it a lot more. There is another book which is very popular, very, very popular these days. It's called Dive into Deep Learning. Right? This book, again, virtue is, it is a little bit of code and a little bit of theory. If you notice, of all the books, is the thinnest. Right? It is the easiest read, and if I may dare to say so, it may be the book, if you really want to get once through the subject quickly and then come back and go deeper, I may suggest that you read this book first. Right? Study this book, run through it quickly, and do that. The last book is, again, a great textbook. It just came out, Understanding Deep Learning. See, guys, some of these excellent books have just come out in the last 2-3 months. Understanding Deep Learning is written by Professor Simon Prince. Great book. There's a bit of an irony about the title, Understanding Deep Learning. In view of what I said in the previous lectures, you remember I said none of us really understand deep learning, neural networks. Right? But the parts that we do understand, the parts about why neural networks are so effective, why they work at all, is very well explained in this book. It's a great book. Huh? So pick your book of choice. Go ahead.
Yeah. Do any of these books go into the infrastructure that's needed for AI?
The infrastructure that's needed for AI is the context of the Sunday boot camp, and it is out of scope for this course.
No,
and
I
none
mean
of
in
these
the
books
books
go.
that you
None of them. None of them. Right? Fortunately, it's a vast field. How much can you talk about in one textbook? So these books, fortunately, most of these books are available free, like legally free, not pirated free. Right? You can go, and these are written by exemplar researchers. You can go and look at the websites of each of these books. You will find slides. You'll find Jupyter notebooks, lots of Jupyter notebooks. You can walk through the code. You can see things. And I encourage you to do that. If you go to this page, you can go to the single view. If you go to the single view mode, then you will see the pictures of these books. And you can look at it like that.
I'm sorry, Asif, I'm not sure if you're sharing it on Zoom.
Oh, I'm not sharing my screen on Zoom. Okay, let's try it now. Is it better? I said great textbooks. I apologize. I should have remembered that.
Yes.
Now, yes. Yeah, now we are. Excuse me. It's been raining here in California, and I seem to have a slightly sore throat. I apologize. So we have these 5 books that I showed you. All of them, they have made a lot of. For example, let's take Understanding Deep Learning, the book that I talked about last. If you go to this book, you will notice that this is a picture, the cover of the book. You go to the website of this book, and you notice that here it is. You want to read the book as a PDF on your iPad or your tablet, your cell phone, whatever it is. The entire book is available free. All the slides are available free. All the Jupyter PowerPoints are available, and Jupyter notebooks are available. This is very much the spirit of sharing. And it's an excellent book. See, guys, these authors spend years writing a textbook. If any one of you have ever written a textbook, you know, it's extremely arduous to write a textbook, and these people do that. So it's kudos to them. All right. So with that out of the way, I'll go back to the course. If you have not joined the Slack, please click on the Slack link. It will get you, it's a Slack invite. It will get you into a Slack. After that, Hamad is here. Let him know. He will make sure that you are added to the 2004 AI particular Slack channel for this course, right? That's it. Zoom link is right here for your reference in future. Your web resources, there are some good web resources, and I will keep adding to this. So, for example, I have added a very good channel for the neural networks. There's a Support Vectors YouTube channel, lectures from the University of Amsterdam, PyTorch Deep Learning Framework, and I'll keep on adding the different web resources that are relevant. As you guys recall, our site was down, and this is all completely created from scratch at this moment. So it will take a little bit of time before we fully catch up. Right. Now, the way you'll see these buttons or these cards that you see on the page, they are all sections. I've divided the sections in such a way that you can tell which day was what. If you remember, the first day was very general. It's like, what is AI? We talked about it at length. Then, if you go in there, you will notice that, sure enough, if you missed the lecture, it is right here. Right? Now, I'm told that I speak rather slowly. And so what people prefer to do is they prefer to, hang on, they prefer to listen to me at 1.5 times the speed. And the young ones prefer to listen to me at twice the speed. Right? Then it feels more young, the speed to them. Right? So your mileage may vary, but if that is so, you can finish the session in an hour. Then you'll see a small summary here. One of the things that you'll see, which I haven't put here, is that there will be a section on quizzes, as I mentioned. We will generate quizzes out of these lectures, and those quizzes should show up by tomorrow at some point for the 2 sessions that have happened. Then you have today, the last time we talked about the first real lecture in which talked about something substantial was the last week, in which we talked about neural networks are universal approximators, if you remember that. Right? Why they are universal approximators is the topic for today. We'll talk about it today. Right? But we saw that they are. If you remember, we went through a lab, we saw there. So here is the video recording, and here is the starter code that you all are familiar with. Right? Does everyone have that? If you don't have it, you can, and since you have access to the portal, you can go download it. Today, we are going to do two things. I left you folks on a cliffhanger. So how does the machine learn? And many of you felt it wasn't quite fair to end the last session with a cliffhanger, say that machines learn, but how do they learn? We'll come back next week. Right? So, well, we are here and we'll learn how machines, we will study how machines learn. This is true not just of neural networks, but all of machine learning. The learning of machine learning is the topic for today. Hopefully a very interesting topic, is the heart of it. Right? What distinguishes a traditional algorithm, let's say quicksort, from a machine learning algorithm? The gist of it is, in quicksort or any other algorithm, you tell the machine what to do. In machine learning, you somehow tell the machine how to learn from the data. And the machine learns somehow, right? Based on how you teach it to learn. It manages to generalize from the data and figure out many things. That is our subject. Are we together? Okay. So we will learn about that topic. Now, the artifacts for today I've already posted on the course portal. We'll learn about this. There's another topic, time permitting, that we'll do, which is also day 3, which is activation functions. What are activation functions? So after learning a gradient descent, after learning the mechanism of learning in machines, we will get much more specific to neural networks. And we will learn about something called activation functions. Are we together? That's the scope for today. If you want to know, and it's a pretty rich topic. Now, for each of these, you notice that I put the web resources. We'll talk about it. There are lots of those of you who know who it is may not have realized that there are close to 400 activation functions in neural networks. It's a very rich field. Right? So if the only thing you know is ReLU and sigmoid, this is a pleasant surprise. Right? There are 400 of those. Then after that, you'll notice that in the course, lots of boxes are black. I put them there because you may want to know what's coming in this course. What are the things that we are going to learn about? If that piques your interest, this is it. This is the set of topics we'll learn. Right? Do we cover all of these in this course? It all depends on you, how fast you folks can move, how fast we can move. Our goal is to understand well rather than to move fast. So we will focus on understanding well. So with that being said, now let's come to gradient descent. So for that, I'll ask you a question on the intuition of it. So guys, if you ever go hiking, I trust all of you have gone hiking, you come across a hilly area. So what do? Suppose you come across a steep mountain. How do you try to climb it? Like, for example, let's say let's imagine that this is a mountain and you're here and you have to climb it. Do you go like this, or do you tend to keep circling around and gradually reach the top? What do?
Latter.
The latter. But when you take a long circuitous route to the top, and if you have ever been driving in mountains, you see that's how roads are. Why do you do that?
It's not as steep.
Not as steep. The gradient is not so high. Steepness, a measure of steepness, people often use the word gradient, or slope. Slope is not high. The slope is very high here, isn't it? But the slope is not so high when I'm circumambulating this hill and gradually going to the top. which is why we circumambulate. But if I were in a hurry to go to the top, what path would I take? Suppose I was not scared of falling down and dying. What would be the steepest path? You would agree that the steepest path would be the shortest. The shortest path is also the steepest path, isn't it? And the opposite is also true. If you want to come down this hill, and let me turn it other way around. If you are here at the top of this and you want to come down to the valley, what path? The shortest path, not a very wise decision. So when you are on top of, let's say, Mission Peak, right, you all agree that it's not a bright idea to take the steepest part down, right? Unless you are in a hurry to break your bones. So you take, again, a circuitous path. But you do agree that suppose you didn't have to fear about getting injured, then the steepest path would be the shortest path. Does that make sense, guys? Right? Shortest path is the steepest path. And that steepest path would be like this, straight down, isn't it? Now, hold that intuition in mind. So what I will do is I'll gradually go from that intuition and now bring it to machine learning slowly. Make sense? At any moment, because this is the heart of machine learning, if at any moment you feel you don't understand, please do ask me the question. I keep using the cliche. If you ask a question, even if it looks naive, you look foolish for a day. If you don't ask a question, then you remain ignorant for a lifetime. Right? So, of course, usually as educators, we tell everybody that it's a cliche. Perhaps if it's annoying to keep repeating it, but forgive me for that. So we are going to now do this. Actually, let me go and see. We already talked about loss function, what is loss, and what is gradient descent, and so forth. So I'll review it again. Actually, let me continue here and review it. So let's see what we talked about the last time. We said that whenever you predict from an algorithm, you make mistakes, right? And when you make mistakes, the measure of mistakes is your loss. It's called the loss function or the error function. Loss function is a little more than error function. It also contains some regularization terms, some new exotic beasts we'll encounter in the course of this workshop. But for now, you can take them to be synonymous. Now, when you have that, the question comes, how do you minimize that? That's the main crux of today. And I sort of left you guys on the cliffhanger. We talked about mini batch. Do we remember what batch, mini batch, and stochastic were? When you accumulate the loss from the entire data set together, it is batch loss or batch learning. When you get it from on the other extreme, when you learn from every instance of data as one step, right? And you go turn the knobs in your machine a little bit. Oh, I got that wrong. Let me turn the knob a little bit more. And then comes the next instance of data, training data. And then you see, oh, how much did I get it wrong? Let me turn the knobs a little bit again. Right? If you do it like that, you're doing stochastic learning and or stochastic gradient descent. And the Goldilocks region in between is to take the middle path, which is that take small batches of data. Right? Why is batch learning bad? Because you have to accumulate all the losses. And if you have gazillions of data, you have to wait for hours before you take a single step of learning. And it may not be, generally, it's a bad idea, not only because you have to wait a lot, but because a lot of those things may have canceled each other out and your losses may not be that great. Mini batch is good. The size is what size you took, 4, 8, 16, 32. Typically, people take powers of 2 as a mini batch size. A mini batch is like a bucket. If you're drawing water from if your data is like a well of water, a mini batch is like a bucket of water that you have drawn from the well. That's how you think about it. Now, so we talked about loss, etc. The whole question that it left with us with is as loss decreases and so forth. But how does loss decrease? How do we make the machine learn? So let's say that you showed it some data. Hang on. Let's say you showed the machine some data and it makes a prediction. This is your xi, any one of the data instances, and it made a prediction by I hat. You already know what the right answer is. You can contrast it with y. Comparing y and y hat, the prediction and the ground truth, you have a measure, some way of measuring the errors. For example, for regression, it was easy. You just, if you're predicting how much ice cream would a young entrepreneur sell on the beach, you predicted 15 gallons. And the young entrepreneur actually could have sold 16 gallons. You underestimated by a gallon. That's a measure of your error, isn't it? It's your loss from that one. And when you accumulate the loss from a mini batch of data points, total loss, you get your total loss, which is written, by the way, you see me write this with a L, peculiar L. It's common. It is, if you, those of you who know LaTeX, it's called the calligraphic L. It's common to use calligraphic L to symbolize loss. And loss is the gap between y and y hat. Right? For regression, it is literally y minus y hat up to square. And then, of course, the summations and all of those things are involved, right? Summation and mean 1 over n. If the number of I is equal to 1 to n, if you have n data points in your mini batch, this is how you would do it. It's the most intuitive way that you could do it. Also, I must say that this was one of the ways. Remember, you could square the losses and get a positive number. You could take its absolute value. By the way, have you ever wondered why square is very common? Those of you who have been in this field a little bit, square losses are very common. Why is that so?
The losses will, I mean, it will be negligible.
It will be negligible. So why is that a good thing?
It won't affect the data set.
Yeah, two reasons. See, the basic intuition is that, as we pointed out, squaring the loss means big losses are penalized. Small losses relatively are ignored, right? Why? It's worth ignoring the small losses because small losses, remember your data, the ground truth may not be the exact ground truth. It also has some errors in it, measurement errors and so forth. So you don't want to be too fixated on the ground truth itself. So small errors are okay. Right? Now, I'll give a formal answer and a lesser answer. There is a formal answer. It's called the Gauss-Markov theorem. Right? It's a mathematical result which says that if you're just doing plain simple regression without any other fancy terms or things added to it, then it is squaring and taking a loss as a sum of squares is the best approach that you can take. So Gauss came up with it a long time ago. We found why. And why is it? So I can give you the mathematics. It's often called also the blue theorem. The blue, B-L-U-E. Forget it if you don't want to remember. It's not that important. It says a best linear unbiased estimator. Quite a mouthful, right? Best linear unbiased estimator. Now, by the way, the biased word takes on meaning from statistics. It's not the bias the way we think of bias. So, but I won't talk more about it, but there is the Gauss-Markov theorem.
So blue is just an acronym for best linear unbiased estimator.
That is it. B-L-U-E. Blue. Right. So, so that's why, if you notice, why is it so common? You can use absolute error, but it is. But instead of telling you the details of the theorem, I'll try to convey the gist of it in a very simple example. See, I'll take it as you all look like parents or have been parented. None of you look like you haven't gone for parenting. So Shrutik has been parented. The rest of you have been parents, perhaps, right? So and Nikita, right? So what happens with parenting? If children make small mistakes, you look the other way around, right? You don't want to notice it. Bad parenting is every single mistake you go, tiny mistake, you go punish the kid, right? So last term is a penalty term. You don't want to penalize for small mistakes. But what do you want to do? If the kid makes a egregious mistake, then good parents come down hard. They don't ignore it, isn't it? Right? So in some sense, that's the intuition behind squaring. Squaring just makes that you penalize when there's an egregious mistake. And when there are tiny mistakes, like just you said, then good parenting says you look the other way around, you don't quite notice it. Right? That's it. That's pretty much the intuition behind this. Now, we'll come to the main topic. Again, let's talk about gradient. So gradient is what? Gradient is slope, steepness, related to word steepness. Steepness, slope. People often use these words interchangeably. No, are we together? It is there. So let's look at this. I'll give you a very simple example. Imagine that now for a moment, get into the mind frame that you have just reincarnated and you find that you're an ant. Right? So all you can do is scroll on a curve. Here you go. You crawl here. Are you together? And by the way, you can imagine that this is a sheet and you're crawling down or something like that. So now, if your goal, let's say that I put a little something sweet here, sugar here. You want to get to the sugar. You can smell it somehow. Or honey is there, sugar, honey is here. And you need to get to this sugar or honey as quickly as you can. What would you do? From here, what is the best path that you can take? Well, you're not allowed to fly. Right? So you're not a winged ant. You can just crawl. Right? This is for all the misdeeds you did this in this lifetime. So now you can only crawl. Right? So you can make a tiny step in the forward direction. Are we together? And when you do if you look at the shadow of this ant has gone from this to on this has gone here. And that is, if you look at the shadow or the projection on the ground, right, then you see that the ant has gone. Let me just call this location. I'll just call this x0 to, let me just call it x1 to x1 prime, isn't it? Has moved a little in this direction. And in reality, on the surface, the ant has gone from x1, y1 to x1 prime, y1 prime. Make sense? That's if you impose a coordinate system upon it. So far, so good, right? So notice, but if the ant, on the other hand, happened to be here, another ant. So this is ant A, and this is your other mischievous friend who has also gotten reincarnated as an ant, right? As B. Now also is racing towards the honey pot, or the honey. Now, which direction can this ant take? Towards the left or towards the right? Towards the left or right? This way. Does that make sense? So this ant also needs to do, and I'll just make it like this. This needs to go like this direction, isn't it?
What do you mean right? There's no way to right.
On your screen, look at it. When you look at your screen, see here. From here, like when you look at the shadow of the ant, look at the projection of the ant down. Right? So the ant is making this journey. See, the ant is making this journey. This is the only thing the ant can do, isn't it? The ant can just make that journey. So what is happening to the shadow of the ant the shadow of the ant is making a place from, let me take this location x2 to x2 prime. So far, so good. So the direction this ant is moving is, in a way, towards the left. And ant A is moving towards the right. Does that make sense? So you say, well, that's pretty good. But suppose the ant, mathematically, what tells an ant to go up or down? How does it figure out? If you tell the ant only one thing, at the bottom is a honeypot. Just say that bottom of your curve is a honeypot. How does the ant know which direction to go locally so that it's heading towards the bottom? Because if it is not careful, a poor ant could be going up. How does it know that it shouldn't go up, A shouldn't go up, that it should take this step down? Because down it doesn't understand. So what you do, now observe something. We will introduce the concept of, and you know all of this, so this will all come very familiar to you. What is a slope? You know, in calculus, in mathematics, we are taught slope. Slope is a tangent. Or more specifically, when you actually drive, and then you say, oh goodness, it's rather slopey. What do you mean by that? Means, would it be fair to say that for a unit distance, whatever unit distance is, one distance of horizontal movement, how far up or down you have been, isn't it? So let's say positive slope is how much you have climbed up. Whatever distance you climbed up for unit, so long as your base is unit, a tiny unit distance, let's say 1 meter, whatever distance you climbed up, let's say you climbed up 3 meters, 3 units, then what's your slope here? 3 over 1, 3, right? If on the other hand, you had gone like this from here, and you had climbed -2, gone down 2 units, then what's your slope? -2, right? You have gone down. That's the notion of a slope. Does that make sense? So now let's observe this point. At this point, if you move, and you always look at slope by going in the positive direction. So if I move unit this, am I climbing up or climbing down? I'm climbing up the slope, up the curve, isn't it? Right? So slope at B, would you agree that slope at B is greater than 0, is positive? It has a positive slope, isn't it? You said that's interesting. Now, what about slope at A? If I move a unit direction here, again in this direction, see in this direction, right? If I move in the positive x direction, the only way I can do that is by going down this slope. When you go down, what is your slope? At this moment, you have lost altitude, right? So you have a negative slope. Slope at B, at A, is smaller than 0. It is clear, isn't it? And it turns out that, see, what is slope? The slope is the amount of gain in altitude. That's what we define. Gain in altitude for a very small movement forward. So if I move a very tiny distance forward, which I will call, because I'm an ant and I can only move tiny little steps, right? So there's a very nice word in calculus, in mathematics, for tiny. We write it as dx. Dx means? Forget this notation. Dx means the tiny step that an ant can take, right? The tiny step that only, the tiny step, the step worthy of an ant, right? Well, I'm talking about ant. How many legs do ants have? 6. So the question is, do they ever step over their own feet? I don't know. This is a question I used to ask my daughter. What about centipedes and millipedes? Do they get confused which of my legs is moving? I don't know. Anyway, so let's say that they move a tiny distance dx. you would move a unit some amount of distance y, isn't it? And you would agree that that is the definition of slope, isn't it? How much did I climb for a little bit of movement forward? And that is all there is to it. I mean, calculus is common sense, guys. Right? And especially it is real life for ants. Yeah? So now here slope is positive, here slope is negative. So now suppose I ask this question, I moved, you see that in this process, I lost delta y because y was here, y1, this is y1 prime, isn't it? This point's y1 prime, isn't it? So I lost this is my delta y for A. And likewise, this one, if I take it here, this is initial y2 and y2 prime. So this is delta yb, right? The gap between these two. Does it make sense? Right? It does make sense. So you would at this moment now observe something very interesting about this curve. Do you notice that when you come to the bottom, how slopey is it at the bottom? It's flat, right? It's like being in Yosemite. All around you are still, but you yourself are just walking along in a flat bowl, right? So you would agree that slope is zero, right? So we'll leave that as a fact. Now what happens is, how do I go? You would agree that this point, x1, if x1 minus x, x1 minus x is delta x, right? Does that make sense? And y, x1 prime is delta x, and y1 minus y1 prime is delta y. Delta y for A, it looks negative. Would you agree? Delta for both of them, it looks negative, right? Now, tell me, if I look at the derivative, look at this slope, which way is the tangent or the slope going? The slope is nothing but the direction of the line that is just tangential to it, right? So the tangent is down, right? If I want to come down slope, suppose my slope is dy or dx at A, right? And I want to ask this question that at this particular moment, if I want to decrease the loss just a little bit, so forget loss, y a little bit, what do I need to do?
What's the question?
If I want to decrease the y a little bit, would you agree that all I need to do is take a little x step at A, tiny step at A, multiplied by that, and then you see that, okay, now I've taken a delta y kind of a situation, right? So if I want to improve upon y, decrease y, in this particular case, decrease y, what can I do? I can go in the direction. This is basically what your situation is, right? Now, think of this way. You look only at the shadow here. Look just as the shadow. The real thing is the ant was here. As far as the shadow is concerned, it needs to make this little journey again and again and get to the bottom. Get to where? Here. And this is the A's journey. And B's journey is, it needs to make, you see these little steps? It needs to go like this. What should it do? What should its new X position be?
The green one or the which one? B or A? B or A?
Either way. So A
It's a small increment.
Small increment, right? So look at this. Should it go, the slope here is negative. So if it has to increase X, should it So suppose I have the slope, no, dy dx. It's some negative quantity, isn't it? I want to move forward. A needs to move forward, right? For A, you need to move forward.
Yes.
Does that make sense?
Yes,
In other words, you want x1 prime for A, so let's say xa prime to be greater than xa, isn't it? Forward direction you want to go. So if you want to go, there's a problem though. Suppose you started out with xa and you want to go to xa prime. Let's think about it. You started at xa, you want to go forward, but your slope at that moment is negative. It's a negative number. So what can you do? You can just take a tiny little step along this direction, right? And a tiny means this slope may be big, but because we are ant, we can take a tiny little step, alpha. Whatever the slope is, slope may be a big number, but we don't have big feet. It's a negative number. We take a tiny step, but against the slope. You see, against the slope. Slope is whatever the slope value is, because it's negative, we need to first make it positive by taking its negative and then take a tiny step in that direction. Does this make sense to you guys? Is this common sense? At A, you would do this. Now, let's think at what would you do at B? xb prime, again, there the slope is, what is the slope at B? Is it positive or negative? It's positive, because a little bit progress in the x direction would cause you to climb up the hill, isn't it? So, well, and which direction do you want to go? Backwards. So to go backwards, once again, you have to go against the slope. So how do you go against the slope? By taking the negative of it, right? So you will take the negative. So suppose you are here, xb, we take the negative, and again, because we are a tiny little ant, we'll take a tiny step. Does that make sense, guys? Are you getting it? Right? So now notice something. What do you notice between these two equations? They look exactly the same. So what does it mean? If the ant had a special antenna that could measure the slope locally, right? If you could measure the slope locally somehow, then the ant can, irrespective of where it is, it can always find its way home to the honeypot. Is it making sense, guys? If this. And so this derivative, therefore, in one dimension is derivative. In higher dimensions, it becomes a symbol. Interesting symbol is the same thing. There's not much difference to it. It is usually written as a generalization with inverted triangle. Right? A little bit more useful than the pyramid.
Atif, I have one question.
Sure, go ahead, sir.
Left and right direction for A and B, that and
Yeah.
both are you are negating. I think A should be positive because we have to go towards zero, right?
Yes, we are no. See, honeypot is here.
Yes.
The honeypot. So A needs to move in the positive direction.
Correct.
So how will it move in the positive direction when slope is less than zero here? At this point, the slope is less than zero. So if you want to go positive, what will you have to do? You'll have to multiply the slope with a negative quantity. Isn't it? You have to go against the slope. Think about it this way. At this point, slope is negative. Right?
Right.
So to move in the positive direction, that number, suppose the slope was -3. How do you move forward? You take -3 multiplied by 3. And then you say, okay, now I'm about to take a step, some proportion of that step. Does that make sense, Sam?
Yes, yes.
That is it. And at B, the problem is the reverse. You want to go backwards, but the slope is positive. And so you again negate it. So in either situation, you always negate the slope. And how do you know that you have reached? Slope is zero. When you take a step and you go nowhere, right? And you realize, oops, you're back to square one, right? So then you know you're done. Does it make sense? right?
Yes,
So,
yes.
so this slope is generalization is gradient. Like when it is a function of multiple variables, like multidimensional, you write it as an inverted triangle. Right? This is also called grad, nabla. There are many names to it in textbooks, but basically this is it. It's just a multidimensional slope.
It's a local minimum.
Which one? In this function, there is only local and global minima are the same thing.
Same.
Right. So now observe something. What we are saying is two statements I'll make. Gradient, if you want to climb, increase your value most, when we generalize it to higher dimension, look at this, which is gradient points to the steepest direction. I'll illustrate this with an example. Actually, why don't I generalize for 2 minutes? But before I generalize, we agree that if you want to go towards the go home, irrespective of what point you are in, your next step should be whatever it is times dy dx. Right? In other words, to go home to the minima, you need to do descent, steepest descent. Steepest, well, there's only one way down. Steepest, in this case, it doesn't make too much sense in 2 dimensions. But if you want to come down, this is your path to going down. Would you agree? Right? This is it. Let's remember this as a fact of life. Right? Now, I'm going to make a statement. Which I will prove now. I will prove that way before Google came up with Google Maps to navigate you, right? Or MapQuest came up with maps to give you directions. In the world of functions, there was a built-in map always. To go home, which we define as a minima point, let's say, all you had to do is take the local gradient, figure out the local gradient. So if you have a function fx and you want to go to its minima as an ant, right? All you have to do is find its gradient or find its derivative and then walk to go to the minima, go against the gradient, to go to the maxima, hilltop, go with the gradient. Like for example, I take this bowl, I want to quickly go to the top, I'm in a hurry, right? So I suddenly turn mountaineer. I start, which is the tangent, which is the direction of the steepest increase, this. I go along the path of the steepest increase. Make sense, guys? That is it. So hill climbing is most efficient in the direction of the steepest increase. That is if you survive it, right? And likewise, coming down is most efficient against the direction of steepest increase, right? Gradient by definition is the direction of steepest increase. One question before I let you come to him here.
How do we pick which X to start with?
You start anywhere, you'll go home. You throw a bunch of ants anywhere on this curve, but you realize that no matter where they start from, if they follow this one rule, they go against the gradient and take their own tiny steps. Soon they will end up at the same point, which is the bottom of the hill. Go ahead.
The one where we go with the gradient, if you go to the steeper curve, on that, how do you determine the slope? Is it like again a tiny one?
That is right. It's very simple. See, suppose you're in the dark. Imagine you're in the dark, and you're thrown into some hill slope. How do you know which direction is steepest? Just take one step in every direction and see which one puts you high or which one takes you down. You can do a local investigation, isn't it? And therefore, you can follow the direction, even in complete darkness. Right? 1 second. Go ahead, Albert.
So if you're not wanting to go above,
Yeah.
from the bottom to above, then it would be just add a plus to that whole equation.
Yes. Then the whole or this equation will change into if you put a plus sign, you're doing the steepest ascent. That is called the hill climbing algorithm. And in machine learning, you use both. Krishna.
Yes, I got the mechanics, but I forgot why we are doing it.
Because we want to. We want to be little ants looking for honey pot. Remember, I told you, there's a honey pot at the bottom. We're coming to that. Yeah. We'll come to that eventually. Right? Okay, guys. So so I'll give you one last piece. What I'm doing is I'm laying the mathematical foundations to get to what we are getting to. Right? We are almost there. Trust me. Now I'll ask you this question. See, just like derivative, we know how to take. So a little bit of calculus. This is nothing but a vector. This is a vector, which is, let's say that you're looking at XY plane, right? Some curve. So let me take some curve. At this point, what is the gradient of this function? Right? It is, no, that's a gradient, remember, is the direction of steepest increase, and we'll come to it. So suppose I have a function. Let me take a function which is x squared plus y squared. This is x and this is y. The question is, gradient will point in the direction in which the function increases the fastest. What possible direction can that be? For any given value of fx, let's say equal to 10, equal to 20, it's a circle. How do you go from 10 to 20? You go radially out, isn't it? This is basically a radius squared, isn't it? If you know your basic circle. So what is the fastest way to increase your radius? Well, go radially out. Don't go against the tangent. Go perpendicular to the tangent, right? This is the only thing you have to know, that in higher dimensions, you go perpendicular to this becomes a contour line. Contour line. Contour lines are lines where the value of the function remains constant. So the moment I said x squared plus y squared is some constant, this function is 10. What does it become? It becomes the equation of a circle, right? It's a contour line then. A circle is a contour line for that function, isn't it? Now, you want to go, you agree that this is the direction it would increase the fastest, isn't it? The function would increase the fastest. Now, let's work it out. If this function is there, it's partial derivative with respect. What is partial derivative? It is to pretend that y is constant. It is, what is it? It is equal to 2x. What is function with respect to y? It is 2y, isn't it? Now, look at this funny vector, xi plus df dy j. You must have encountered vectors ij in high school, isn't it? What does it look like? It looks like 2xi plus 2xj, 2y j, isn't it? Now, it turns out that in machine learning, people don't write vectors like that, because soon you run out of ijk's. When you're talking in 1,000 dimensions, English letters don't quite serve you. So people have a notation. They just write it as f dx df dy as a column matrix, a column vector. We call it a column vector. Vectors are written as columns of numbers. The first one is your ith, this is implied as jth, right? So now tell me one thing. At this point P, what is the coordinates of this point? Right? What is this point is x and y, right? Another way of saying is that this vector, P is the vector, your dual interpretation, P is the vector going from origin to that point, isn't it? And what did the derivative turn out to be? The gradient turned out to be? The gradient of f turned out to be, at the point P, turned out to be 2x, 2y. Isn't it? Basically twice P itself. So if P goes in this direction, in which direction does the gradient go? In the same direction. It just happens to be twice as big. Isn't it? And if you look at this direction, it's radially outwards. Isn't it? Again, speaks to the fact that gradient points to the direction of maximum increase. Keep this important. We'll need this throughout this course. Gradients point to the direction of maximum increase of any function. So that's a takeaway, guys. Right? And it is always perpendicular to the contour lines, which by definition are lines or curves or surfaces where all values of a function are the same. Right? So for example, if I take a sphere, the surface of a sphere, if the function is x squared plus y squared plus z squared, what can you tell about the surface of that sphere or that ball? It's a contour surface, isn't it? Because radius remains the same on that sphere. Does that make sense, guys? That's it. So, and gradient points perpendicular to that surface. So for example, when you launch a rocket, what do you want to do? You want to gain altitude as fast as possible. So do you point it in this direction, or do you point it perpendicular to the earth? Straight up. Why? Because that's the gradient. That's the direction of the steepest.
How do you come to that 22x when it's going to linear? The space is going to keep on increasing. How do you come to that 22?
At any given point. So the point is x and y. If I'm looking at this function, take its derivative. You see it's 2x to y. Take the derivative. See, look at this. Partial derivative of x just means pretend y is constant. What is the derivative of x square, if you happen to remember? X square is 2x. It's just a fact of calculus. But ignore the 2. It doesn't matter. The basic intuition I'm trying to do is that in the world of functions, there is a God-given Google map. It's called the gradient. So long as you keep a gradient in your pocket, it's your compass. It can always take you home. Right? So always carry gradients with you when you're in the function world.
So probably I forgot the math geometry, but the x squared plus y squared being a circle, right? I'm not able to relate. How is that happening?
Oh, see, in a circle, let's say that this point, right? This is the x, this is the y. Notice that if I increase x, I'm coming down the circle here, and I'm increasing y, I go up to this. But the definition of a circle is that the two squares add up to 1, because that is exactly what is x. So look at this. At this point, this part is x, this part is y, isn't it? Do you remember your Pythagoras theorem? What does it say? Hypotenuse is?
Oh, yeah, okay. No.
Right? So hypotenuse, which is the function fx here, or the radius squared is x squared plus y squared. Easy, right?
Okay. Now I get it. Thanks.
That's that. All right, guys. So lots of takeaways. And what does this all have to do with machine learning? Good heavens, that's a question. Who was asking? Krishnan was asking. Yeah, the MBA, the executive, he's asking, what are we talking about? Get real. All right, we'll get real. So the takeaways are: you want to come to the honeypot at the bottom of the valley, go against the gradient, because gradient takes you as high, as fast as it can, high up, right? For any functions. And now I'll just mention one thing. See, I keep using the word functions, but I keep drawing curves, isn't it? So there is a relationship, guys. Geometrically, algebraically, what is a function? Geometrically is a curve in 2 dimensions, isn't it? When you write y is equal to mx plus b, what is it? Equation of a straight line. Geometrically, it's this. There is a curve in space that it corresponds to. And so you can reason about things either geometrically, visually, or algebraically. Now, it turns out that I am deeply biased towards geometrical interpretation. And that geometric way of looking at things is something that you'll find that theoretical physicists tend to do a lot, quantum physicists tend to do a lot. Are we together? Right? You don't have to. In fact, in computer science, like if you read your typical computer science textbook, it tends to be, in my view, and I may be wrong, or it used to be, now a little bit more visualizations coming up. It used to be heavily algebraic. But I find that intuition is better if you just think geometry, right? And develop intuition like that. So all of this lessons we take, and now we come to our world. Let's bring it down to machine learning and to the learning of machine learning. I hereby claim that I just taught you the learning of machine learning. How is that possible? We have to connect the dots. We need to build a bridge. Are we together? So let's build a bridge. See, guys, suppose data presents to you as these points. I'll take these points. And I'll take a very simple example. In 2 dimensions. This is your data space. And for reasons that is convention in the family, in machine learning, you always say that, okay, so this is your X, this is your Y. Are we together? Input is X, output is Y. Response is Y. Now, the way this is the data space. Would you agree? This is the data space. You can literally visualize the data as is. Are we together? Now, let me introduce you to an entirely different world, an imaginary world. It's somewhat like Alice going off to sleep and waking up in the Wonderland. So let's go to another.
So, for my answer is the one which like the fancy.
It could be anything. Like, or for example, yeah, you can pick, you can put an intuition to this data. Right? It's data, right? And now you need to do, and then let's go to another magical world, right? And for me, actually, I always tend to carry this childish intuitions. It's like because of all the stories that I read, Alice in Wonderland. So it's just the Wonderland. So there's the Mad Hatter and right, and Tweedledee and Tweedledum, and all of them are there. So and there is another world that will come to. I call it the hypothesis space. Hypothesis space, a magical world, hypothesis space. Right? Or like the Wizard of Oz. Right? And in this world, imagine the access is. So now tell me one thing. If I ask you to make the best hypothesis, first you have to pick a class of hypothesis. Looking at this data, what would you say is the best relationship between Y and X? A straight line, geometrically a straight line. So it is some straight line. Let us make an assumption. It's a hypothesis. That hypothesis may be true or false. And this is important, guys. Machine learning, you first make a hypothesis because you think so. The hypothesis on experiment may turn out to be right or wrong. But if you make a hypothesis that a straight line can fit the data, can describe the relationship between input and output. If you could fit a straight line to the data, you have a prediction model, right? For any given X, now you can predict Y, right? So your hypothesis would be Y hat is equal to, in terms of school language, MX plus B, right? Or MX plus C, depending upon whether you were taught the British way or the American way. Right? I think the two conventions differ in school books like this. What is the B or C? It is the intercept, right? And what is M?
Slope.
The slope. Now, there's a slight change of convention when you come to the machine learning community. They tend not to use this notation. They tend to use, so here is something that they use, which is quite common. And then deep learning community sort of turns it on its head. In much of machine learning, things that are real, that can be observed, can X and Y be observed? Let's say that, let's make it real. X is the temperature of the day, temperature on that given day. Y is how much ice cream a young entrepreneur would sell on the beach. Are we together? It's an amount of ice cream. So these are measurable quantities, right? These are empirically measurable quantities. So there is a convention in machine learning that says that when you deal with empirically measurable quantities, you use Roman letters. What are Roman letters? A, B, C, D, E, Roman alphabet. When you are talking about abstractions, concepts, pieces of concepts, the things that help you formulate a concept, you use Greek letters, right? So let's pick beta or theta. So you'll see we can pick beta or we can pick theta. Both of them are common conventions. You'll see in machine learning textbooks. For the sake of it, I'll just take beta. So I'll write this equation as beta naught plus beta 1x. Right? Beta being your B or C, whatever slope. This is the intercept. And what is beta 1? Slope. Right? And then we can generalize it to higher dimensions. For example, in 3 dimensions, the line would become a plane. In 4 dimensions, it will become a hyperplane. Right? It will keep becoming a hyperplane. But let's leave it this way. So now,
sorry, what? How is the intercept?
intercept of a line is, given a line, this is the intercept. When x is 0, how high is that line? Right? This height is intercept, is the definition of the intercept. And slope is, again, we talked about slope, the steepness of it. Right? So we are together. So now, you know that on this page, you need to draw a line that will, there is one line that will best fit the data. Right? What is that line? Let's say you could draw, and you don't know what that line is. So in this plane, you can draw lots and lots of lines. And let's say that you draw a line like this. Let me draw big fat lines. Suppose I draw a line like, this is my first hypothesis. Let me call this hypothesis A. You say, A is the relationship between input and output. You seem to be rather off base, isn't it? You can say, well, somebody else comes up and says, no, the real relationship between this is, there is no relationship. This is it. B. Y just doesn't respond to X. Right? Or something like that. The third one can go and say that, hey, you know what? It isn't, you guys are all wrong. The real relationship is like this, C. And the fourth guy, happen chance, makes the guess that the real relationship is this, D. Now, which of these is the best hypothesis? D. And how do you quantify that? You quantify any hypothesis by saying that, see, the data points, if you look at A, there is a huge gap for any given X, huge gap between theory and prediction, isn't it? This gap, there's a word for it. These are called residuals. The prediction errors. These are your Y minus Y hat for that point. Let's just say the ith point, right? So you would say that you have big residuals. So in fact, you square the residuals, square. That would be huge, isn't it? And if you do for the for let's say the A line, would you agree that this quantity would be huge, right? B would be better, C would be even better, and D would be the best, isn't it? So therefore, this quantity, which is called the loss, is minimum for D. But here's the problem. Suppose you don't have eyes, and you randomly plot a line, and then you measure the loss. And now the question is, that loss can increase or decrease. How do you know that you are at the best line? If you are at A, what can you do to discover D? So there are many ways of doing it. There are some clever ways, and then there are some not so clever ways. So to give you an idea of a clever and a non-clever way, let's start with the non-clever way. So you guys have all learned about bubble sort, quick sort, merge sort, and all the sorting algorithms, right, in college. So, but there is one big sorting algorithm which takes the cake, which will always underperform your other algorithms, even bubble sort. So how do you sort that? Suppose you have a bunch of numbers and you want to sort it. What do? You just shuffle them, and then you stare at it. Is it sorted? Oh, it isn't. You say, oh, shucks. Okay, let me shuffle it again. And you keep doing it forever. But you know, this algorithm will terminate, right? It's a valid algorithm because it will eventually converge. It will eventually stop. Someday you'll discover that it is all sorted. So that's your, should we call it bogus sort? Bogus sort. That's one simple algorithm. In the same way, you could, for example, go on drawing random lines on the page and seeing which of the lines gives you the least loss. Is that the approach we should take? No, why not? Because they are, in sorting, actually, shuffling, there are actually finitely many permutations. In machine learning, the situation is much worse. There are infinitely many lines you can draw on the plane. So you can just go on, and you will never know whether you have hit upon the right answer, isn't it? You'll never know. And so it turns out that there is a trick. Here's the trick. And this brings us to the concept of this hypothesis space versus data space. So I'll redraw this thing. These two worlds, the real world and the dream world, the Alice in Wonderland world. So I'll draw these points again. And you would agree that irrespective of what line you draw, let's say this is your hypothesis, this line has a intercept beta naught and a slope beta 1, isn't it? Every line is a hypothesis about the answer, about the relationship, isn't it? This is your data space. Sorry, let me write it in black. This is your data space. Let's go to the hypothesis space, whose axis, it turns out, in this magical world are beta naught and beta 1. So you agree that for every line here, what is it in the hypothesis space? A point, right? So here, beta naught looks positive, beta 1 looks negative. So it is some point here. Let me call this line A. So would you agree that A is this point? Isn't it? A positive intercept, a negative slope, right? You draw another line. Let me take this line. Oh, sorry. Let's try a better color. So just to distinguish it. This one. Now, the intercept is negative, slope is positive, right? So this probably, and slightly negative, slope is very positive. So would you agree that the green point B is here? The line B in the hypothesis space is a point. You agree? And so on and so forth.
That's a quick question. As you're drawing the line, would
Yeah.
the direction of the line matter as well with an arrow, or just a line?
No.
Because when you define the intercept being positive, negative, and the slope being positive, would the direction matter?
Well, no. Line, well, the way we think of line is, they have infinite extent. They go forever and forever in both directions. So the only thing that matters is, two things matter. When x is 0, what is the value y? That is the intercept, right? And the second thing that matters is, if I increase x by 1 unit, how much does y increase or decrease on that line?
Okay.
Right? So that is the intercept and slope. That's the only things that characterize. So you say that they are sufficient to characterize a line, these two parameters. Right? So, and therefore I introduce the word parameters. The beta 1, and beta naught, these are the parameters of your model, of your hypothesis. More commonly, hypotheses are called model. Are we together? People commonly call them as model in the field of machine learning. Remember, every hypothesis is that, right?
Asif, can I ask you a question? So the initial line that is picked for basically starting the process is random and it's just an intuition, right? I mean, is there any magic way of finding the initial?
No, you shouldn't bother. You shouldn't bother. Pick something at this moment. Well, later on, I'll qualify the statement by saying sometimes try to be a little bit careful, but generally, you don't. The math here is pretty powerful. It will take care of you. And so, guys, do you notice that if I were to draw a third line, let's say I draw this line again has positive intercept and positive slope. So it is some point like this. C. By the way, I'm not being absolutely correct. But you realize that somewhere in there is one line, orange line, with a positive intercept and positive slope, which is your best answer. Let me call it D, which is your best answer, isn't it? So what is best about it? What happens is that to each of these points, you can associate a loss, right? A loss function that depends on the hypothesis, depends on the line that you chose. So it is a function of beta, isn't it? The choice of beta, beta naught, beta 1. beta vector, right? So if you take beta vector as beta naught, beta 1, it is a function of loss. Loss is the thing. At each point, you can measure the loss at C, loss at D, loss at B. And we do know that the loss will be lowest at D, right? So now let's do one thing. Let's go to the third dimension. Let's redraw this thing in 3 dimensions. Remember, imagine that you have a floor. The floor has, you can move backward and forward, left and right. These are the 2 directions of the floor. Right? This is your floor. Does it look like a floor, guys? Checkered floor? Okay. This is your floor. And let's now add one more direction. It is the loss itself, the loss function. So you agree that for every point, if I pick a point here, this point corresponds to, this is still the hypothesis space. People, I call it the hypothesis space, more formally, to use more formal language, is the parameter space, or parametric space, whatever it is, parameter space, right? There, associated with each point anywhere, there is a loss associated with it, isn't it? Do we agree? There's a loss. And now what you notice is that the loss here for straight line, for a straight line hypothesis, and I'll give this to you as a fact, you can convince yourself that this is true. It is shaped like this. And I'll explain to you why. But first, at this moment, take it as a fact that it is like this. Oh, does this look like my bowl?
Yep.
So it is like this bowl. Beautiful. And we know, suppose you take a random point. Suppose you happen to take this point as your initial guess. Let me call this A. And you end up, let's say that A takes you all the way up here. This is the projection. Up here, this is the loss associated with A. Now tell me, what is your best hypothesis? It is that choice. This is the perfect answer, isn't it? You're in search of this answer. Because at this point, the loss is lowest. Do we feel like becoming ants now and crawling to the answer? Right? And how do we do that? Did we develop the mathematical machinery to do that? Right? So what do? At this point, we just say, hey, what is the gradient of the loss? I happen to start at A. If I know the gradient of the loss, then I can move in this direction, because I'll be climbing down, 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 down. And that will be creeping in, the shadow of the ant will be creeping straight to the honeypot, the best line, isn't it? And what would you do? What is the ground made up of? It is just happens to be made up of the beta parameters. Whether you take beta naught or beta 1, doesn't matter. Let me say beta 1, if you so want, beta 0 is equal to whatever previous value of beta there was, minus a small step, because ants can take small steps, the gradient of the loss with respect to beta naught. Derivative of the loss with respect to beta naught, partial derivative. Likewise, beta 1, your next location should be, right? Beta 1 minus alpha, gradient of loss, beta 1, isn't it? Or more formally, I can write it as beta next. The next value of the beta should be your previous value of beta, whatever in vector notation, minus alpha, gradient of the loss. Isn't it? That's what it is. And this is, folks, the honeypot that we were chasing, the Holy Grail. This is learning of machine learning. You see? You're trying to find that point in the hypothesis space where you have which is the best hypothesis, where the loss is the lowest, mistakes are the lowest. Are we getting it, guys? Sure thing.
So just to be clear, in order for this algorithm to work, you'd already have to know the correct loss function. Like it doesn't help you.
Yes. So, and where does the loss function come from? See, the loss function comes from this. Now let's work out the rest of the math How do you know the loss function? You made a hypothesis that the relationship is this. This is what you made the hypothesis. Using this hypothesis, you can make a prediction, y hat, isn't it? For any point. So let's say that you're given a point, I. For the ith point, you will say y minus y hat squared for the ith point. This is your error. This is your loss for that one term, isn't it? And you can sum it up. So if you don't mind, I'll ignore the summation over I and averaging and so forth. Remember, what did I tell you? When you understand, what should you do? You erase out all the subscripts and superscripts. Just like I told you in physics, like, you know, have you seen this equation? Right?
Mm-hmm.
So whenever you write this equation, theoretical physicists will know that you're not part of their community, because they wouldn't write it like that. They will just write it E is equal to M.
Yeah.
They say speed of light is 1. They just erase all the constants. Because if you stare at this equation, it intuitively conveys the gist of it, namely mass and energy are exactly the same thing. Right? Much more directly it conveys without the clutter of C square there. In the same way, in machine learning, I would advise you that all the superscript and subscripts, you can, for the time being, just forget about it. Bring them in later, summations and so forth. So if you just look at it, y minus y hat, I'll just write it like this, right? Are we together? Now let's look at this.
Is that the least square?
It is, so yeah, that is it. If this is the loss, it is the sum squared loss. The least square is exactly the least value of this loss. That is it, Madhav, right? So now look at this. Y hat is given by beta naught minus beta 1 x, whatever the point is. Let me just bring that up. So this square, right? This is loss is made up of summation over this. Forget about the summation and the superscript. Just pay attention to this part for the time being. Let's pay attention to this part. When we look at this part, now remember, guys, data is given, isn't it? Data is given to you. What are you trying to do? You know that you want to fit a straight line to it. All that you're allowed to do during the training part to find the best fit line is to just move the line around. When you bend the line around, turn the line around, what are you changing? Beta naught and beta 1, right? And what about x and y? Those are the observations. You don't fix the observations. If you do that, that's cheating, isn't it? So I'm reminded of a real incident that happened to me when I was in IIT. We had the first lab, and you know, as always, first year college students are given a pendulum, and they're supposed to calculate the value of G, gravity. We had a person, I won't name it because he's now a really big shot in India, right? So what he did is, he looked at the textbook. It said G is equal to 9.81, and then he cooked up the data. And then he said, my lab is done. He didn't put in any effort. So then even the lab technician, who was barely high school pass, he also told him that, sir, this is not right. He asked, what's not right? It's right. Well, too good. And actually, which was the problem. And it also happens to be the fact that in Benares, where it was there, G is not 9.81. Right? You're not at sea level, you're not at the equator. It's different. Right? So a little bit like that. You can't fudge with the data and make it fit your hypothesis. You have to keep the data there and find the best hypothesis, the best value of G. Right? So what changes is beta naught and beta 1. But now look at this. What is this? It becomes a quadratic, and this is a part that you have to observe. It's a quadratic equation in betas, either beta naught or beta 1. Do you see that this equation is a quadratic equation in that? Also notice that since it is a sum of squares, can it ever be negative? Can the loss ever be negative? The smallest it can be is 0, which it usually isn't. But the other thing is, what is the maximum value it can achieve? Infinity. Just take really bad hypothesis, isn't it? You'll get terrible answers, right? Close to infinity.
Is that the reason why the loss function is quadratic?
That is why. And now you saw, I just argued and told you that the loss function, the algebra, says that it is positive, right? It's quadratic positive and goes up to infinity. What is the one quadratic surface that goes off to infinity? Does it look like this bowl? And did I draw a bowl here? Right? And thus, you get the intuition. Are we together? Go ahead.
What is alpha equation?
It's a small step. It's the step that it's the amount of, what is it? The stride length of an ant. But if you don't like to think in terms of stride length of an ant or how far one ant can make a step, and you prefer more formal language, let's call it the learning rate. This is the learning rate in machine learning. How fast are you learning? Right? Now, that reminds me, why should we be ants? Why shouldn't we take giant steps? Anybody can see a reason? Why should we not take giant steps?
You may miss the law.
Yes, you can miss it. If you try to get too smart, right, you might end up here, you might end up here, you might end up here, and you'll just keep bouncing around and never reach the minimum. Right? So that's the argument against too big a step. What's the argument? Therefore, should we take the slowest, tiniest 10 to the 1 billionth of a value, tiniest atomic steps, like, you move one atom forward. Would that be a good idea?
No.
Why is that not a good
It will
idea?
take a long time.
It will take you forever to get there, right? So it reminds me of myself, actually, when I used to work at Siebel and Oracle long ago in a previous lifetime. So we would go for lunch, all of us colleagues. We were there in Emeryville, and we would go to Berkeley for lunch. So some people go fast, some go slow. Nobody wanted to come in my car. Guess why? By the time I would reach there, others were coming back. Right? So you don't want to go that slow either. So there is in between a Goldilocks region, right? A good learning rate. And the technology of figuring out a good learning rate in machine learning, that whole thing is called learning rate scheduler. We will learn about it in the neural networks. Right? In this course, at this moment, we are laying foundations. But by the way, guys, this course is going to pick up speed like anything. Right? So remember, I told you that story about devil and the hell? Anyone remembers? No? Blank faces. Okay. So one day, a guy had done equal amounts of good and evil, apparently. So Angel Gabriel was all confused. Should I put him in hell or heaven? So I gave him a choice. Go sample both and tell me where do you want to go. So he went to heaven, and he noticed that people were very good people. They looked rather boring, right? And sitting there doing noble things. And then he went to hell, and there was excellent coffee, right? Great food, great music, excellent company. So he came back and he told the angel that I think all things considered, I'll prefer down there, hell. But the moment he committed to it and he went down, the beating started. He said, what? Why is this? And there the devil said, well, then you were a visitor. Right? You were just sampling, and now is the reality.
This is like joining a company.
Right?
The interview
So in the same spirit, I remember the first 3 sessions were supposed to be tastes. So you just got a taste of that, hopefully, and now the meetings will start.
I said, now it's will be like that.
All right, guys. So I'll give you
one
guys.
question I have. So there's something we talked about the reward and punishment during the learning.
Penalty.
Okay.
Loss is the penalty. Loss is the penalty. You want to minimize your model has a certain penalty, how much mistakes it made, and you want to minimize the penalty. Because in this context, they are synonymous. But I suppose what you're thinking of is a different form of machine learning, which will come to at some point, that also is based on this theory, reinforcement learning, which is based on carrot and stick. But let's hold that. They're all based on the same theory. Right? Okay, guys. So with that, I will pause. I hope you have understood gradient descent and loss function. Right? What is loss? Where does the loss function exist? It exists in the Alice in Wonderland world of hypothesis. Remember the other world that you can't see. what you can see is the data world. You can visualize the data world and so forth and so forth, right? Yeah, the world of observations, empirical observations, is the data world. But hypothesis, the moment you make a hypothesis of how the output relates to the input, right? You are now making a hypothesis in the hypothesis space or the parameter space, where hypothesis is built out of parameters. Therefore, you give them Greek letters, and those parameters can change. So anywhere in the hypothesis space is a point with the lowest loss, the best answer. And how do you find that answer? Fortunately, loss is a function. Because it's a function, it's a surface. Because it's a surface, therefore you can go to the bottom by doing gradient descent. Are we together? Now, let's take a 5 minutes break, and through a Jupyter notebook, I'll make all of these things ready. And no more than 5 minutes, guys.
Asif, you're still recording on YouTube.
Let's just we'll leave it on. Otherwise, it becomes two different videos.
Okay. I just pinged you a link in the chat. There is a good simulation if you want to just check that.
Yeah.
That's why we saw many things. That's what we saw. They reminded them that.
What is the symbol? So book and class. So you have to register. It's a separate. Then you go to explain.
How do they register?
Assembly register.
If you want to use that, you can go to the rules, you give the rule, you just set it and you enroll in it.
Okay, always complete. Back to Google. Yes.
Oh, okay. Just look at that. Oh, okay. Oh, the first thing.
Oh, no, no, all right, guys. By my clock, 5 minutes up. Time to ring the bell. Okay. Guys, ready? 1, 2.
Asif, there is a question in the chat. If you wouldn't mind, I can read it.
Please do.
It appears that in this ant exercise, we know where the honeypot is.
Right.
Hence, we know all the moments and relative to that honeypot. However, in a real problem where we don't have the final destination, which is honeypot, how do we ascertain that that the direction we are moving is taking us closer to the target?
See, what we know, now let's relate it to machine learning. Right? We know that our solution is always the point of lowest loss. Right? So honeypot was a mental construct just to say we are searching for the point of lowest loss. We don't know where it is. Right? Just as an ant, let's say, cannot see. It doesn't know where the honeypot is, but it has one rule. It is going to do gradient descent. And so long as it does gradient descent, it is guaranteed to end up at the point of lowest loss. Does that answer the question, then? Whichever is asking. See, what you're searching for is point of lowest loss, and gradient descent will take you there.
In the example of ice cream, it's basically how much ice cream was sold is the honeypot, right? Because that's the no.
Yeah. No, a prediction model that predicts the amount of ice cream sold almost to the dot.
Right.
It is the most prediction model has the lowest loss, and that loss value is the honeypot you're searching for, practically speaking. Right? You don't want to overestimate, you don't want to underestimate. You always want to get the ice cream that you will sell on a given day as right as possible. Otherwise, the entrepreneur, she is going to lose money. If she overestimates, gets too much ice cream, it goes waste. If she gets too little ice cream from the wholesaler, then she has the unenviable pleasure of seeing a competitor. All the clients go to the competitor.
Asif, I'm sorry, but I see Madhu replying to SR. Madhu, I think the right way to say it, I think you said the ice cream sold from the past, but that's not what it is, right? It is the amount of ice cream that we should order so that we will maximize the sale. That's no unit is left is kind of what we are trying to achieve. How much ice cream do I order given this temperature is what that honeypot number is. It's not from the data set from the past, it is the future.
No, but you learn from the past. You learn from the past, and you want to make
sure. But the honeypot quantity is not the data from the past, right? That's what I'm trying to say.
Yes, you're right. And then what you do in reality is, suppose you have all of this data, right? You partition the data. You call one part the training data, and you train the model only on this. This becomes the past data. This you hide under the pillow, and you call it the test data. And what you do is, you need to, when you're modeling, you don't show it to the model. It will find the minima here, the lowest loss point on the historic data. Then you want to make sure that the test data sort of is the proxy for future. In your language, is the proxy for future, and it better have the lowest loss for that test data. And also, in the next few days, when you sell ice cream in the future, it should have the lowest loss or lowest discrepancy between prediction and reality.
Just a logistic question. We are out of coffee, so I can make coffee. Yeah. But how many people need it? So
yeah. Okay, guys. How many of you are going to have a cup of coffee? We will make fresh ones. Maybe 6, 7. All right, guys. So now,
just one question. The data what we plot for the
Yeah.
strike rate. So it happens to be a strike rate. because the data was like that.
Yeah.
In the real world, the data may not be like fit to that
Okay.
straight line, right?
Yes.
So there could be some random thing. Okay. I don't know.
That is true. In other words, the data could be fit to this curve. We saw that in the lab, if you remember, last time in the law episode. So now this is a good question. Who would like to answer it? How do we make all this theory work for this curve?
Is the loss function that we are trying to minimize.
It's just your hypothesis. So here's one easy way to think about it. This curve is a polynomial, right? So you can write this curve y hat is equal to beta naught plus beta 1 x plus beta 2 x square beta k x to the power k, a k degree polynomial, right? Yeah. Because you do. So why did I pick polynomial? I'll tell you a very basic rule of algebra. It's something that sort of people don't quite notice. Think of polynomials, degree of a polynomial and shape. A straight line is a polynomial of what degree?
1.
One. It's a polynomial of 2 degrees. Now, what about this guy? This curve? 3. Sine wave, for example. So you can think of it like that. Square plus beta 3 x cubed. Suppose I bring in, what about now? 4. You can convince yourself this will do. So the trick is count the number of bends, and your polynomial degree should be 1 more than that. So how many bends there are in a straight line? It's straight. There are no bends. 0 bends. So it's a polynomial of degree 1.
2.
2.
1 bend. Sorry, 2 bends.
Yes. You see the relationship between geometry and algebra. This is something actually I wish math was taught like this. It's such a beautiful subject, very obvious subject it is. But see, this is so now look at your thing.
One question. I mean,
Before you go there, let me finish the thought because people are waiting for it. So suppose you make a curve. You agree that there is some polynomial degree that will fit to it, right? Some degree. Let's say how many bends there are? 1, 2, 3, 4.
5.
Where's the 5th bend? Yeah. Oh, so polynomial of degree 5. Right? That could be a good way of fitting it, approximately. Right? Now, by the way, there's a flaw in the argument. So if there's a mathematician here who is just about to jump off his seat, hang into your chair. Right? So you have a polynomial of degree 5. And now I'll tell you, you can write it as y is equal to beta naught plus beta 1 x1, beta 5 x5, isn't it? Now, think of it this way. Imagine a 5-dimensional space. It's very easy to imagine a 5-dimensional space. Right? 1 axis, 2 axis, 3 axis, 4 axis, 5 axis. So the ground has 5 directions you can move. All of them are perpendicular to each other. Well, it's not a real world, but it can exist. And arising out of it is the y. So this is x1, this is x. One axis is x, one axis is x square, one axis is x cubed, x4, x5. What is this equation? This is a linear equation in those 5 axes, isn't it? Those features. A linear equation always represents a straight hypersurface, hyperplane. And therefore, what in 2 dimension looks to you like a curve happens to be a plane in a 5-dimensional space. So now from that, I can generalize that any curve, there is some space in which it is just flat. And in fact, you're just searching for it. What you just did in 2 dimensions, you can write a loss function in this particular dimension. I'll give you a very sort of a cheesy way to remember it. Have you noticed that no wonder how mischievous you are? In the eyes of your doting mom, you're perfectly straight. There's no crookedness in you, right? So in the same way, no matter how crooked a curve is, ups and downs, there is a mother dimension in which the curve is absolutely straight. All right? So hold that intuition in your mind. And so all of this theory works.
So even in that the higher polynomial, when you got that like the loss function with the parameters, what we did for the stripe.
Yes.
turned out to be like
It will be. It will
it's
be.
a parabola.
It will be a parabolic.
So when we look at like from any dimension, that space like there'll be like a parabola.
Yeah, go to some higher dimension, you'll find yourself. That's why, where is it? That's why these bowls are eternal and universal. I'm kidding. Right? They're very good. Both. There's always a bowl in some space. Go ahead. Come down. Okay.
What about some of the sphere where we would actually
No. This is no. This is, it's hard to imagine, but I'm imagining a 5-dimensional floor, right? Rising above it is Y. Now, how do you imagine 5-dimensional floor? You imagine 2-dimensional floor and very loudly say, as you can see in 5 dimensions.
because I was telling because we are talking only the X component, not the Y.
No, Y is the vertical direction. Right? Just like in 2 dimensions, Y is the vertical, you typically put it, right? So now here, look at this. Loss function is the vertical dimension always. So here, what are your X dimensions? You see, this is the equation of a plane, right? Right. And so the loss function of this will be in a 6-dimensional space, 6-dimensional, because there's beta naught also there. So in a 6-dimensional floor of a hypothesis space, or parameter space, you have beta naught, beta 1, beta 2, beta 3, beta 4, beta 5, beta 6, right? Oh, no, beta 5 isn't. And then rising above it is the loss direction, and in there is a parabola sitting for you. Make sense? That's it. That's all it is. Right?
It's a surface. Right?
It's a surface, exactly. It's a empty. So yeah, don't think papaya. Just the outer shell of the papaya, right? Yeah.
Where does the so let's say if we want to radically stab at this, like how do we select the betas?
Come again.
How do we select
You randomly pick one and do gradient descent. Remember, in this surface, the beautiful thing is, don't worry where you start from. Start from here, but you will eventually come down. Gradient descent will take you down. Remember, what did I say? When you get lost, what do? Immediately you say, okay, where is my navigator? But I'm saying in the world of mathematics, people didn't have to wait for Google to come around. There was always a navigator. What was it? It was the gradient of the function. So in the function space, there's always a gradient. Right? In this case, this is the loss function. So there is always a gradient of the loss that you can have.
The problem would be, I think, if you did not estimate the number of betas correctly, the polynomial.
Oh, that's right. That is right. And that brings you to the whole point that, see, machine learning always solves half the problem, never the whole problem. You have to pick a class of algorithm and then you let it figure it out. Right? And that is where actually, so I give you a very simple thing called linear regression, where the loss function was actually, it had a global minima, it was parabolic. And now I'll let you, now it was just to, training wheels. And now I'll show you a more realistic loss function. I think I showed you guys with hills and valleys, complicated loss function. It still looks like a parabola. It still looks like a bowl, but quite big, right? With hills and valleys. And that's how neural networks are. But let's come to that, guys, now. I want to get to that stage and bring this whole thing. It all looks very theoretical and fun, but actually you'll realize in a moment that this is very real. How many of you know the Old Faithful Geyser? Have you been to Yellowstone National Park? What's the Old Faithful Geyser? Anyone? It is the hot spring. What is its property? What is its defining quality?
It's timely.
Yes, it does, right? It does indeed. So I want you guys to do this. Let's make this real, guys. Huh? Otherwise, it's of no use. Why am I on this page? Let me get rid of this. Guys, please pay attention now. See, guys, you see this picture. This is more realistically what a loss landscape is like. But before we go there, I want you to introduce you to things. First of all, guys, look. Oh, sorry. This is too big. Does this equation now make sense? Is it obvious what we are talking about there? Theta next is equal to theta naught minus alpha, gradient of the loss, right? That's all it is. Now we are going to do something. We are actually going to look through some data. And the data we'll look through is, by the way, before I go there, I posted all of this just for your reference. Everything has been posted to your class web page. Once again, before I do anything else, let me remind you that you need to import this data, download this labs, run it locally so you can see all of this in action. You see gradient descent, guys? Go to gradient descent. You will notice that gradient descent on Old Faithful Geyser, you see these files that are there? Are we seeing these 6 files, guys? Just add it to your previous project that you downloaded last week. The same directory, notebook directory. Are we together? Right? Please do that. And I will go over these one by one now carefully. First of all, what is the Old Faithful Geyser? It is this. Oh, sorry. This is, I don't know why it's doing. It is this thing. It's a rendering. It's an artistic rendering of it. It's a geyser that faithfully keeps erupting every once in a while. Now, the way it works is that the geothermal phenomenon is that under the ground, steam builds up. When the steam builds up sufficiently, then suddenly through a fissure, the whole thing comes out. Right? So now what happens is when it comes out and it erupts, and the longer the eruption, the more it gets depressurized, isn't it? And then, therefore, the longer it takes for the pressure to build up again for the next eruption. Does that make common sense, guys? This data is often used as one of the first practical data sets in machine learning courses. So this is it. Eruption, how long were the eruptions and what's the wait time for the eruption, right? So if you look at it, this is the data. Eruptions is the length of the eruptions and how long you have to wait. So you have to predict how long you have to wait for the next eruption, right? By looking at how long this eruption is. By the way, we have our own Old Faithful Geyser here in Napa, Calistoga. I don't know if you guys know. Right? You can go there. So this is a lab I borrowed from a previous, another course, a more basic course on data. So you can imagine this is a statistical description of the data. You can build a regression line. What is a regression? Splitting a straight line. Is this beta naught and beta 1 we were talking about? Our hypothesis would be that there is a straight line relationship between wait time and eruption. The bigger the eruption, the longer the wait time, isn't it? So we can make a hypothesis like that. Oh, what is that epsilon? Is the irreducible error. You know that we'll never get it right. We'll never get it perfect. But reality will be our hypothesis plus some error. Right? What is our hypothesis? Y hat is equal to beta naught plus beta 1. Is it making sense, guys? Beta naught plus beta 1 is our hypothesis. Okay. And now, I hope this whole thing is visible to everyone on the screen. And don't show again. If you were to do, if you were to use code, let's say scikit-learn, you can fit it. You can see that the intercept is close to 0, slope is close to 1, right? Which sort of matches if you happen to look at the data. Slope is close to 1, right? And intercept is close to 0, right? It sort of seems to go almost to the 0th point. So I'll leave it as that. Now, can you do this without using linear regression? Can we write the loss function ourselves? So this is basically linear regression, the easy way, using somebody's library. And since we are trying to learn machine learning from scratch, let's try to do it without doing all of that. By hand, let us compute the loss function and do gradient descent of the loss function. We should be able to do that, right? We just learned the learning in machine learning. So why rely on libraries? Let's go and do it on our own. So I've checked in a few files. You can look at it, by the way. I've given dB scan clustering and k-means clustering, etc. Here is the visualization of the this thing. What we will do in this time around is we will compute the gradient. This is what we want to do. Beta naught is the previous value of beta. The beta is the next value, is the previous value minus alpha times the gradient of the loss. Is it making sense, guys? Right? It's totally making sense, right? Parameters. What are the parameters? Slope and intercept. Beta naught is the slope. Beta naught is the intercept. Beta 1 is the slope. And what is that alpha? It is the tiny step that the ant can take. Learning rate, right? The learning rate. That is the loss function. And how do we quantify the loss function? Y minus y hat squared. That's why it's called the sum squared loss. And your solution is called the least square. Yeah. Principle of least square. Yeah, getting the least. And so, well, this is basic calculus. You can compute out the gradient of the losses as a mathematical expression. When you do the gradient, this basic quadratic equation, you will get this. Beta naught next should be this and this. So now we know how to do it. So we should be able to implement it ourselves, run through the data again and again, and keep taking these tiny little steps through the data, isn't it? Towards the loss, and see, literally, you see me do that.
I said, a little bit. Did you add the plus alpha? I thought we were subtracting the alpha.
Then the gradient to the step is, remember, there's a minus here. Yeah. So minus of the minus becomes a plus. Right? You see the minus here, right? That's why it becomes a plus. And so we take a learning rate, 10 to the minus 5. By the way, that's about as big a step as a little ant can take, I suppose. 10 to the minus 5 meters. By the way, 10 to the minus 5 is a good starting point. You can go more aggressive, you can go more conservative. I take it as a default. Oh, by the way, in this example, I must have been in a hurry. I took it 10 to the minus 4 eventually. Okay. You take a random values of beta naught, beta 1, but for the visualization purpose, I cheated. I took a value so I could show you the gradient descent in progress. I deliberately took values far off. Really bad values, really bad guesses. Right? I'm going to iterate through that. So do you see me epoch? What is an epoch? Epoch is one cycle through the data, one iteration through the data. And oh, by the way, you see me use, do you notice that I'm using, what am I doing? I'm using Roman letters in the code for data, for observables, and Greek letters for parameters of my hypothesis.
That is all a positive value. Negative value is the graph. Positive image where the data is there.
Yeah.
It all shows the positive values.
Well, nothing. No, remember, this is not of the data. I'm in the hypothesis space. Remember, you are right. That data that you are referring to, and this is why I say distinguish between hypothesis and data. This is the data space. Hypothesis, I just choose to believe that the slope is negative. Or intercept is, who's going to stop me? I can make as bad an assumption as possible, right? Yeah, deliberately I did that. Like, you couldn't have chosen a much worse starting point, in a way. Yeah. I am saying I'm not looking at the figure. I'm totally blind, and I'm just making a guess. Right? I'm saying even if you do that, you'll still get it. So, guys, let's look at this code carefully.
Question on that graph. I mean,
which graph?
The one that you were showing on the, yeah, that one.
Yes.
Yeah. So it looks like a polynomial, right? I mean, there are two things going on.
No. There are two clusters there, but you're trying to fit a straight line. You're trying to predict waiting time based on eruption time. So as the eruption time goes up, waiting time also goes up, right? Look at this graph.
Right. And what is the size of the bubble? I mean, how does that?
Yeah, so that's a geothermal phenomenon. What happens is that you can have either short eruptions or long eruptions. Yeah, and there's a bit of geophysics there, but we won't go into it. So ignore the fact that there's clusters there. Actually, that's what the other two notebooks were, to find the clusters in the data. Go ahead. Yeah. No, all we are saying is weighting is a function, some function of eruption. What function is it? When you look at this picture, you can clearly see that if eruption times go up, waiting time goes up. That's it. And we are finding a relationship. So we make a hypothesis that it's some straight line relationship. That's it. Are we clear?
This is a question from online. Just one question. So going back to that, the hypothesis you just made, waiting time versus the height of the eruption. What if you're trying to look for another question, right? If you're asking a different type of question on the same data, would the equation change? Like if you
yes.
said, okay.
We ask a very specific question. How do I predict waiting time based on the timing of the last eruption? That's the question you answer. Yeah, you're trying to answer. But yes, on this data, you could ask many, many questions. Like, for example, what are the two clusters? Two different kinds of eruptions, short eruption, long eruption, right? You could ask many, many things actually with this data, but we're asking the simplest question. Right? Does that answer you?
It does. I'm only wondering how the equation would change if you ask a different question, the correlation between the question versus the equation.
See, any equation, you have to write it as a relationship between input and output. If you can do that, then the rest of the math remains exactly the same. Yeah? You have to write it, as I said, as a hypothesis. Yeah? A line, a curve, some function. And then you find the best fit function. That is why often machine learning is also called function fitting.
Got it. Thank you.
Okay. So we take this, and guys, look at the code. I hope the code is quite literally everything that I've been talking about. Greek letters for parameters of your hypothesis, and Roman letters for actual observations. So I'm just taking what is equation here, this equation, I've literally written it up in code. No. So what do? You first compute the gradients. Then once you have computed the gradient, then you can take the gradient descent step, isn't it? You can. This is computing the gradients is more like computing the total loss for that. And then, because you're summing up over all of this, and then I should say compute the gradients based loss. Then taking the gradient of the loss and taking the step, and then updating the loss function. Because now you have new values for your beta. Right? Your beta has changed. So you have a new hypothesis now. What is the loss for that hypothesis? You need to figure out. And then that is it. And as you do that, gradually what happens is that your loss function, you notice that gradually, if you look at beta naught, what is it doing? You chose some random value 4. It is gradually, rapidly converging towards epoch after epoch, it's improving. And it seems to be converging towards 0, close to 0. You know that was the right answer for beta 1, right? The intercept was close to 0. Likewise, for beta 1, if you remember, the slope was 0.91 or something like that. So let's see, where is it converging? Look at this, epoch after epoch. As you go on training it, where does it go? It goes towards 0.91, right? Or point something, right? So both of the parameters converge to the right answer, what does that mean geometrically? And if you look at the loss function, beautifully, you see the loss function for every epoch. Rapidly, it learns in the beginning, and after that, it completely slows down. In fact, it starts crawling. It doesn't improve anymore. What can you say at this point? What is the gradient of the loss at that point?
0.
Yeah, 0, very close to 0. So when the gradient itself is small, and you take a tiny step on the gradient, you're not going to lose much altitude, isn't it? It's like walking around in Yosemite and wondering, am I getting close to sea level? No. Right? So that's that. So let's look at the contour surfaces for this. Contours are like projections of all points on the loss surface. How do they look on the ground? They will look like this, isn't it? Yeah. If you look at this bowl, what are the contour surfaces? They will look like this. So circles, circular like, right? And so now let's see, is this the picture that you have in mind? Isn't it? And so if you randomly started at this point, this was your initial hypothesis. Do you see where my mouse is? So the loss was this much. Remember, I chose this, right? 4 minus 4 or something like that, or 4 and something. Yeah. I took this deliberately, as bad an answer as possible. So it leads to this. And gradually, as the ant comes down that bowl, its shadow goes down straight to the right hypothesis, the best hypothesis, isn't it? And so I'll show you the animation, guys. Observe this animation carefully. By the way, all of this code is there. And as you can see, this code is not hard. It's just basic code. And I'll run this. Keep your eyes pointed to this, guys, this point and the shadow down. So I'll start it. What do you notice? Do you see the ant making its way home, right? Making its way towards the honeypot. And do you notice that it slowed down? Why has it slowed down? Because closer to the base, at the bottom of the bowl, close to the bottom, there isn't much slope. There isn't much of a gradient. So it slows down. Right? And there you go. Right? So that is gradient descent. In real terms, that's what gradient descent is. Now, any questions, guys? I don't know. I want to make this very real. How does learning in machines take place, guys? This is learning, except that it doesn't happen in the data world. It happens in Alice in Wonderland, you know, the Wonderland of hypothesis space, right? Or the land of Oz, right? So if you have read the story, The Wizard of Oz, what does Dorothy keep saying all the time? No place like home. So she's all the time making her way home. Well, you see, this gradient descent or this loss function is Dorothy trying to find her way home. Yes.
So you said that it slows down as you come closer to home.
Mhm.
But the steps that the ant is taking is always the same. Right?
No. Yeah. So what it is that you have a learning rate, but you multiply it by the gradient, and then the product becomes tinier and tinier and tinier. So you creep your way to the bottom, which brings in the whole technology in neural networks and in machine learning called learning rate scheduler. When should you take bigger steps and when should you take smaller steps? Right? And there are many, many schedulers that you will learn about in the optimizers.
Question here.
Yes.
Isn't there a danger? I think there's a danger where the ant gets stuck in a local name.
Very good. I'll come to that question now. That is absolutely the question. So this is fine for linear regression and polynomial regression and so forth. But what about real life? Let's see what real life looks like. Once again, guys, I've given you all of these links in your course portal. Where in the world is your course portal? Yeah, here it is. So guys, look at the third link, loss landscape, isn't it? Let's click on this. And let's explore. And I think I've shown you this visualization before. Neural network loss landscapes are much more complicated. Do you see how complicated they are? They're local minimas and local. And one of the problems, actually, neural network at one time were practically abandoned. The reason is that they say, well, the loss landscape doesn't look like a nice bowl with one minima, global minimum. Right. So these kinds of surfaces are called convex surfaces, right? If you ever are in doubt what convex surfaces look like, look at your tummy. Right? So convex surfaces, right? So they have one minima, only one minima. But if you look at the loss landscape of these, you realize there are many minima, and for many years people abandoned it. Today, and neural networks have actually gone through many winters. People thought you couldn't get out of that, and they created all sorts of theories to get out of that. Today, we know we can there's a lot of technologies to get out of it. And now the joke is the other way around. The neural network crowd looks at those old critiques and say that they were suffering from convexivitis. So let's not suffer from convexivitis. There is a cure for that. There is technology that gets you out. But that's a topic of, guess what? Optimizers. And if you look at your course portal, you will notice that, sure enough, when you look at your course, oh, look at that. There's a topic called optimizers coming soon, which will teach us how not to get trapped in local minimums. Right? Okay, guys, so with that, I would strongly suggest you guys use this code, play around with it. Is the code simple, guys? Is it something that you would feel comfortable? Remember, we have all the TAs to help you and walk you through the code if needed. Right? So you're not alone. It's not like Udemy or Coursera where if you're screwed, you're screwed. No, we are there to help you. Reach out to us. We will guide you through, take you forward. It's important that you reach out to us. We'll take you forward. Any questions before I close the chapter on this?
So essentially, if this, what you're projecting here is when the next, for how long we wait before the next election is going to happen, that's what it was.
Exactly. And it will, at the model that is at the bottom of this, here, is the model that builds a line that is the best fit line. That is the best fit line. Namely, it will be the line that is, that, for example,
given yes, it will predict Y.
Yes, it is this line. At the bottom is the hypothesis, that is this line. Are we together? That's it, guys. That is, if you get, I've deliberately chosen a very simple example, but this is machine learning, the learning of the machine in machine learning, right? So what does machine learning go on? It walks on two legs, guys, just two ideas, roughly speaking. And all problems ultimately can be quantified. You need a way to quantify loss or defect, errors, use your term. Once you have quantified that, you need a technology to minimize this, isn't it? And have we now covered both? Right? We have covered both. This is the foundation. Now I would like to take, oh, we are already at 9:23. As you guys all agreed, we'll be here for till 11, right? Okay, now I'll summarize it. I was going to cover activation function also, but we'll do it next time. But guys, from next time, the pace will pick up. Huh? Next time, we'll cover activation function and another topic called back propagation. Right? So we'll get deeply into neural networks. So today is the end of the foundations. Now we will get into neural networks specifically. Right? And we will do one neural architecture after another in rapid succession. Right? So I hope you enjoyed it. Now, let me summarize. We set out to learn what is learning in machine learning. And I hope we did. What are the ingredients of machine learning? First is you quantify, you create a loss function. And then there's a mathematical tool called the gradient, which very nicely takes you to the minima of that loss function using a process called gradient descent. Right? Whatever point you reach, whatever hypothesis is there at the bottom of that loss surface is the pot of gold. That's where your rainbow ends. Right? That's the thing your machine is searching for, the best hypothesis. That is it, guys. I'll open it up to questions. I hope it wasn't too confusing. I know that these are very new concepts. Any feedback, any questions, any confusions?
In the code, we started like epsilon, which is the irreducible error.
What is that? Where does epsilon come from, guys? Anyone?
Error rate, tidy error to differentiate between
Y and Y hat. But why is it there? Why is the prediction model never absolutely right?
That would be cheating.
That is like that guy who starts with the value and then does it. So no, the reasons are there. First of all, no measurement is absolutely accurate. Yeah? Instrumental error. Like you don't do that every day, right? Every morning you get up out of your bed, you stand on the weighing machine before getting into the shower. You don't like the value, you just get down, knock it a little bit, and get on top of it again. Right? Hope for a better reading. Right? So that's instrumentation error. But epsilon also contains something deeper. It is a measure of that which the model doesn't know, but it should know. It is the unknown unknowns. So for example, if the entrepreneur has made, so let me talk about irreducible error a bit. If the entrepreneur has made a model based on just temperature, part of the reason for irreducible error would be temperature is not the only thing. whether it's a holiday or a work day is another big factor. But your input, your model doesn't know about it, hasn't factored that in. So there will be a bar for the same temperature. On the days when it is a holiday, there'll be far more sale of ice cream. Parents will bring their kids. On a work day, parents are serving their grandmasters, right? So they are not taking kids to the beach. Sale of ice cream will be low. So you'll see a band of error, right? For a given day. So remember, irreducible error captures also that the unknowns, the things that are unknown for the model, factors that the model has not. So whenever you see a big irreducible error, it should give you a clue that you might have missed the main point. Right? So for example, I'll take an example. Suppose you want to predict how much ice cream will sell on the beach, and the entrepreneur believes that it has everything to do with, let us say, let's say that there's some game being played, right? I don't know, the stock market, right? It is whether NASDAQ is up or down. Reasonably good hypothesis. What's happening out there in New York Exchange is affecting how many kids come to the beach. Now, what will really happen? There may be some signal in there, tiny, but you'll have a huge irreducible error, isn't it? Why? Because you missed the main point that temperature may be the biggest predictor. After all, ice creams are cheap. Even in a recession, parents bring their kids to the beach.
So is there a way for the model to know that you have missed this parameter?
Generally, when it is giving you a high irreducible error at the end of the model, that should be a clue that you don't know enough. That's the biggest clue.
It could be any type of.
Oh yeah, it cannot know. It's like us, right? We don't know. Yeah. Like there's so many things we don't know.
So you really have to like basically keep experimenting to see which is the parameter.
Yeah. One good practice in machine learning always believe that you know only the partial reality. Always go with the feeling that you have a small window into the world. You only understand things partially. Never believe you have all the factors accounted for. Ever. Right? That's that. All right, guys. Questions? Any questions?
When you say, let's say how do we know that we missed a parameter? Like, because even if we miss a parameter, the gradient will be reasonable.
Please say that again.
So how do we know?
Oh yeah, you wouldn't know. Your hypothesis. See, the machine will find the best hypothesis given your assumptions. Right?
So in the next experiment, I just pick random other parameters
also and keep trying. Keep trying. There is more method to it. There are ways to weed out bad parameters, bad factors and inputs and pick good inputs. Suppose you take a brute force, like let's pick 100 inputs. Most of them may prove useless, right? So for example, if I make a hypothesis that adult onset diabetes depends upon which colored shirts people wear. So you might keep the color of the shirt as one of the factors predicting people's A1C, the hemoglobin A1C level, which is a measure of diabetes. But after a little while, you'll realize that it's not really a good predictor. Right? So you will end up weeding it out. Right? Or somebody else may believe it all depends upon how many penguins jumped on that day off a iceberg into the sea might affect your diabetes. Who knows? I mean, people ultimately believe all sorts of things, right? But then the data may not support it.
So,
question.
Yeah. Anything?
Is there a mathematical model to read such?
Yeah, there's a lot of machinery. So I'm just taking you straight to neural networks, but there's a huge amount of beautiful machinery that exists, and we can talk offline about that. So yeah, let me take the offline. Let me take those. Lots of people on the remote. Yeah, please go ahead.
As a question here, right? We have defined y as a function of x,
Right.
which I assume is a single like temperature versus ice cream. The
Yes.
moment we go into talking about the same example where you continued, whether it's a holiday or not, and and other parameters that we would have to add, what is that function going to look like? Is it still
Yes,
written
the
as
vector
a
function.
function of X?
Yes, yes. Only thing is your definition of X changes. See, in machine learning, arbitrarily, the definition of X is first factor, second factor, third factor. It's a vector made out of P factors, P input factors, right? So it is, and therefore Y hat is a vector function of X. That's why you realize that a lot of machine learning is vector calculus and linear algebra. That's it.
Asif, do you want to quickly remind everybody to register for the course from next session onwards? That's important.
Oh, yes, yes, guys. So our first 3 sessions, they were like the devil giving a good ride to hell, right? No, I'm kidding. So these were the first 3 sessions, guys. It's a premium thing. But now, in deference to the people who have actually paid and registered, the rest of you, if you want to continue, please do register. Please send me a note. We are keeping track of who has formally registered and paid the tuition. The rest of it, you have to pay the tuition for. Okay? And if you are not, if you intend to move on from here, then thank you for being part of our learning journey so far. And I hope you enjoyed it, and I hope you benefited from it. And those of you who do want to register, may I suggest that you can go register on the website, but PayPal takes a huge cut. We run more or less a low margin, no profit, no loss teaching initiative here. So you're better off sending us a check or sending the amount by Zelle. So that part I should mention. If you Zelle it to this number, official number, 2989030. This is your Zelle amount. And if you send it by check, send it by check to support vectors, and our address is on the website, support vectors, and our address is, you can send it to 46540 Fremont Boulevard, Suite 506, Fremont, California, 94538.
What was the amount again?
Oh, yeah, the big thing, amount is $1,600.
Yeah, and you can find all this information in the email that Kate has sent, and I've also pinged in the chat in case if anybody wants to take any screenshots and stuff.
All right, guys, any questions? No questions on the chat?
I had one question.
Hold your local question because you are here.
Atif, I have one question. Sorry,
Yeah.
I don't want to look stupid all my life. Today is okay to admit it. I'm very, very sorry. I'm not very mathematically strong. So if you can take us to intersection and gradient slope. I understand why slope is positive or negative, but I did not still catch a full essence of why intersection is considered negative in case of B.
Oh, it's very simple. Imagine that you have a line. You have this XY plane, right? XY plane. Suppose I make a line. Let's make any random line. Let's say A. Now from origin, this is the origin. Here, do you have to go up or down? If you have to go up to meet where it hits the y-axis, you say intercept is positive. If on the other hand, I make a line like this, now here, from the origin, do you have to go up or down?
Down.
Down. So you say, this is it. This is this. These are called intercepts.
Okay. Got it. Completely got it now.
Intercept is, this is it. That's all it is.
And slope in once more for my thing. Slope is here positive and negative because the line is how we determine
Yeah,
the slope is positive or negative?
yeah. Slope is, just imagine that you're going in the positive x direction.
Okay.
And look at the line. If you were an ant sitting on the line and going
Mhm.
in the positive x direction, is the y increasing or decreasing? For A, y is, suppose you are here.
Increasing for A is increasing.
Yeah, right. If you go in this direction, height you gain. So this is
Yeah.
slope is positive. For this, the slope is negative. And then suppose I take a green line, let's
Understood.
say this line, here the intercept is positive, but the slope is still negative.
Understood. Now it's all clear.
Yeah.
Thank you.
You're welcome. I hope you're having fun, Sam.
I'm having fun. Only thing is, still I get nightmare that my chancellor is asking me to revoke my employment because I am failed in mathematics.
That's not going to happen.
Good one.
See, math is the most obvious, dead obvious and easy thing in the world. Everything else is hard. Programming is hard. God knows what bugs are hiding in the code. Life is hard, right? Business is hard. Relationships are hard. But math is the easiest thing in the world.
Dude, you are making it definitely easy to understand. Our teachers made it definitely like a sound like a printing machine where people are not even understanding, but they are printing the problems.
Yes. Yeah, that's right. See, the trouble with math is math. See, in India, they say that spiritual knowledge is an oral tradition. You hear that statement, that it can only be conveyed from person to person. In the West, people very strongly believe that math is an oral tradition. The right way to learn math is to learn from somebody who really understands it so well that for him everything is obvious. I'll tell you something. In mathematical communities, there is something called the Erdos number. Have you ever heard of that Erdos number?
No.
Most people in our community have a Erdos number. They know what their Erdos number is because Erdos was a great mathematician and a great teacher. And his students were brilliant. And the students were brilliant enough. And so far it goes. Now you can often tell, there's a legend, there's a belief that you can tell how great or deep a mathematician is by just computing how many links away he's from Erdos. So we all have a Erdos number. It is an oral tradition. You don't learn math from books. Never learn math from books. You learn math from a friend who is good at math.
Couldn't agree.
Which is why I'm here, Sam. That's the purpose I'm serving to you.
Yeah. Thank you, Philip. Feeling really supported. I remember me early days in teaching computer science software and taking similar efforts to explain logic. But math was never in my grip.
Well, this is fun. You'll realize, like, once the fear of grades and other nonsense goes away.
Right.
Beautiful subject and very obvious. Actually, everything is clear and simple in math, unlike other fields. All right, folks. Any other questions?
Sir, this is Sri. One more question. How does one arrive at a loss function, right? I mean, we're asking so many questions of the data, and based on the number of variables that go into that question, the loss function is going to change. How do we ascertain that the loss function we've developed or postulating is the right answer or is the right equation for the answer we're looking for?
Yeah. See, if you're predicting a number, right? Let's say that it's a regression. Whenever you predict a number, the process is called regression. Right? For example, predicting tomorrow's ice cream sale, tomorrow's temperature, anything. Whenever you're predicting, right? Or how many, like how long will your car run before it breaks down? Things like that. You're predicting a number. Whenever you predict a number, then you take some historic data, you make predictions on those without seeing the answer, and then you compare it to the answer. Then, so there will be a reality, ground truth, there will be a prediction that you made, and the gap between the two, therefore you can create a sum squared loss, right? Because you can, a y minus y hat, reality minus prediction squared will be your thing. And it doesn't matter how you build your algorithms, what hypothesis you do. At the end of it, that is your loss. Now you need to relate that loss to whatever particular hypothesis you took. So today I took linear regression. It is the kindergarten of machine learning. And it is the workhorse. Actually, it is the most used algorithm in machine learning in actual practice, right? Outside things like audio, video, natural language processing, etc. For tabular data, linear regression is still ruling the roost. But when it comes to very complicated things, to which this course alludes to, we will make highly nonlinear models. We'll use neural networks. But even then, the loss function remains the same. It's just that the pieces of our hypothesis become different. They become the weights and biases of neural networks. But it is still the same loss function and will work with the same loss function. Ultimately, is the gap between prediction and reality.
Got it. Thank you.
Asif, the quizzes are not yet up on the
Oh,
Intro to
yes.
AI course portal, which
Yeah,
should
they
be a
are
lot
not.
of fun.
Yeah, that should be a lot of fun. I'll start uploading the quiz, guys. Just rebuild the whole portal, and it's a work in progress, let's just say, because the AI engine has to run and produce your quiz on the AI settings. We'll do that.
Asif, will there be any in-house TA sessions where we can come in
They'll be over Zoom.
over Zoom?
Over Zoom.
And how do we request them?
We'll announce a few, and others you can get as a one-on-one.
Okay.
But we'll announce a few. In fact, quite likely today I'm too tired, but tomorrow I should announce a schedule of those TA sessions. And I would strongly encourage, see, I can teach only the big ideas, and a lot of the things I deliberately miss because I know that the TAs will cover it.
And will there be any homeworks further down?
Oh, yes, yes. Now, right? Till now, like I told you, right, the first three were without meetings. Now you'll have sessions which will have little homework. I mean, I'm joking, of course. There will be little projects for you to do, little things to do. Those are coming. At this moment, we're just laying the basic foundation. So the first three sessions are basic foundation. Now we pick up speed. But having said that, the Jupyter notebooks that I've released, just making them run and playing with them. If you haven't done that, please do that.
Where can I read more about the loss function and how you alluded to the? I don't want to read the entire book. That's why I'm asking for that 10%.
Okay, yeah, very good question. Actually, thank you for asking. I'm still waiting on you. Guys, may I just point out that there are some excellent resources that I forgot to mention as part of this. Before I close, let me do that. Where's the course bar? So guys, here, today was gradient descent, right? So if you go there, 3 blue, 1 brown, they have an excellent page. You see this video here? Watch the video and read the article beneath it. It will reinforce whatever I taught you. In fact, most likely it's done a better job than I did. And then this is one. The other thing that you should do is loss landscape visualization. And then any one of these books, just read that loss function chapter. It's a short chapter. Right? It won't be that big. That's it.
And one last question. Like, who do we approach for the Sunday book? Like, do you want to?
No. So guys, those of you who want to register for the Sunday boot camp or who are not registered, walk over to my office. I'll register you. Right? Okay. Any more questions remotely, guys? Otherwise, there's a question waiting in house. Go ahead. Your question.
Oh, my. So I think we touched a little bit on that in the hypothesis space.
Yeah.
Let's say we have no idea. The data is so complicated, we have no idea what the order of the polynomial is, whatever. We just picked the regression. Turns out to be like a 7-degree polynomial, but we're just using 2. Obviously,
then you'll have a lot of irreducible errors.
Correct.
Exactly.
So how do we get started with a good number?
Yes. So the thing is, whenever you pick an arbitrary point, like a second-degree polynomial, remember the degree becomes something called a hyperparameter of the model.
Correct.
And so then you have to do hyperparameter search. Build the best second-degree polynomial, build the best third-degree polynomial, build the best 4-degree polynomial, and so forth, till you
Is that
find
a
the
brute
polynomial.
search or is
So, well, the simple answer is brute search. The better answer is there's a whole sophisticated theory of Bayesian optimization and upper parameter search.
what did you say? Which of
Bayesian optimization. So there was a brick called
Bayesian
Bayes.
optimization? Got it.
Yeah, Bayesian optimization.
Yep.
Right. But let's sort of walk before we run.
So, but just plotting the data,
Yeah.
from there, can we do some guesses?
Yeah, the guess is you can, well, that's that. Yeah. Okay, guys, give me a moment. I'll be back. Yeah, hang on.
Yeah, well, Asif is away. I just wanted to let you guys know that end of this course, once you register and finish it, there will be a certificate that you can actually post through your LinkedIn channels and stuff like that. So we'll provide a formal certificate of completion.
Yes, that's true. Really good to post that on LinkedIn.
Thank you.
Kate, by chance, do you have ability to reset the passwords on Learning Portal, or is that still Asif?
The Learning Portal, I can check if you're on there. And one of the tricky things is that you need to know that the login usernames are set as lowercase first name dot last name, not your email address. That's the first thing. And the default password is set to supportvectors.123 with the first S uppercase. And then you're supposed to change it the moment you log in. Are you not able to log in?
I am not able to. I was able to before. I'll try that in a second. Thank you. You said all my first name, last name is lowercase, is it?
First name dot last name, all lowercase. I'll send you a Slack message too.
Thank you.
I had a similar question. I will be sending the amount using the Zelle information that Asif showed. After that, I will go to the portal, use my first name dot last name lowercase and default password support vectors dot 123 as capital. Is that correct?
Right. Right. If you're in the course portal, you should be there with your username as your lowercase first name dot last name, and then that same default password that you should change the moment you log in.
Perfect.
Yeah. All right, guys. If any other questions on record, otherwise I'll stop the recording.
Oh, crap.
Oh my God.
Did you just reveal your social security number?
No, just the password.
Oh, it's all right. We'll chop it off the recording.